share screen and okay. Yeah, this, so quick reminder that I've already removed one of the practice problems, one of the problems from the weak acid, weak base titration off of the homework. So last class we were talking, oh jeez, sorry. Last class we talked about how to do a buffer problem. We also talked about acid-base titration. We started talking about like looking at the curve, a strong acid, strong base titration. You see really sharp lines, and then the pH, the middle point right here, the equivalence point is right here at 7, and then it's sharp up here. It's a very small change in pH during the titration, and then finally huge change with the equivalence point being how much, where the moles of acid and moles of base are equal. So that's what we talked, and then we talked about how to do calculations, which you may see some of these calculations in the homework. Not sure how much we'll actually see on the test, but you break them down into these 4 steps. Step 1 is you calculate your moles, which is just molarity times volume. You do the ice table to neutralize acid with base. Step 3, you redilute, because when you've added volume of base to volume of acid, the total volume has changed. So your concentrations will change because of that. And finally, then you just do pH equals negative log of H plus. So that's what we did last class. We kind of cut it a little bit early because of how things are going with, but okay. And then we actually did a practice strong base with strong acid titration. So let's do one more. Well, practice, I'm going to titrate a strong acid, a strong base with a strong acid. So let me go ahead and write some stuff down. We have our base. We have 15 mils of our base. We have 0.75 molar acid, and it says it takes 10 mils of acid to neutralize base. Okay, so what is the pH at 0, 5, 10, and 15? We want to go 0, 5, 10, 15. So we want to know what's the pH of our base under these conditions. First thing we need to do is calculate the molarity of base, because you're not given that. This would be like our lab, one of our labs that we're going to do, that I have done, where I'm going to titrate a known, like a base with a known acid, or an acid with a known base. You'll use the equivalence point to determine what is the concentration of our known base, unknown base. So how did we do that in General Chemistry 1? We said Ma Ba equals Mb Bb. You can do that real quick. So we have what? For acid, we have 10 mils of acid with a concentration of 0.75, neutralizes 15 mils of base. So what is our concentration of base? You divide both sides by 15, and you get the concentration of base. The molarity of base has to be 0.5 molar. Okay, We have everything we need to do this now. So step one, at zero amount of acid added, what is the pH? Well, since it's a strong base and no acid is added, it is not a titration. It's just negative log of OH minus would give us our POH. So negative log of 0.5 would give us a POH of 0.3. But because I asked for a pH, you're going to have 14 minus 0.3. So a pH of 13.7. Got to remember, since the base is in an overabundance, we're going to start having to deal with the OH first. Okay, next step, 5 mils. So it's an ice table. I, C, E. There's our base. Here's our acid. So with 15 mils of base at 0.5 molar, the moles of base would be 7.5. 7.5. At 5 mils of acid at 0.75 molar, the amount of acid is 3.75.
Where are you getting this from?
I'm saying, so M of acid times B of acid. So 5 and 0.75. And the 15 and 0.5 is not going to change. The 15 and the 0.5 right here. So the molarity of base we determined as 0.5. The molarity of base is 0.5, and there's always going to be 15 mils of that base. There's always going to be 15 mils of that base. That's not going to change. That's our starting concentration, our starting amount of base. But we're going to slowly add more and more acid. So when I add 5 mils of acid, 5 mils of 0.75 gives us, we've added 3.75 moles. Conveniently, for the math, that's exactly half. So we have 0 acid left and 3.75 moles of base. Now, what is our concentration of hydroxide? That's moles, but molarity is moles divided by volume. So I went from 15 mils and I added 5 mils. So 15 plus 5, our V total, 15 plus 5 is 20. So 3.75 divided by 20 is going to be 0.8 equals 0.1875. So what is the pH when hydroxide is 0.1875? So negative log of 0.1875 gives us a POH of 0.726. 0.726. But remember, POH, we have to turn it to pH. So 14 minus 0.726 gives us a pH of 13.27. So when I added half of the amount of acid that would be required to neutralize it, we still have very little change in the amount of OH. So I'm just trying to make some room. Okay, so half the amount. Now the second, so that's the second pH at 5 mils. At 10 mils, 10 times 7.5 would give us 7.5. You have 7.5 molar of acid, 7.5 molar of base. They cancel out. You'd have 0 acid and 0 base. They have completely neutralized. What is the pH of a strong acid, strong base when they're completely neutralized?
7.
7, yes. And so that one, you don't have to really do any math if you recognize that is the equivalence point. And then finally, the last point is when I add 15 mils of acid to our base. So 15 times 0.75 is 11.25. Now there is more acid than base. So base neutralizes all of the base is neutralized by the acid, and there is 0 base left and 3.75 molar acid left. Now we've added 15 mils of acid to 15 mils of base. So 15 plus 15 is 30. So 3.75 divided by 30.
Where you get the 15 from?
So 15 is how much acid I've added, and 15 mil of base is the original amount of base we started with.
Okay.
So it's the volume of acid I added to the volume of base that was originally in solution.
Okay.
So with that in mind, the molarity is 0.125. The negative log of that is 0.9. But because this is acid and not base, means we don't have to convert this. So the pH at the 4 points is 13.7 is our starting point. 13.27 is our half equivalence point. 7 is our equivalence point. And then 5 mils afterwards, it drops down to 0.9. So we see a huge jump from one side to the other. And that's indicative of our strong acid, strong base. Now, as I said, this is fair game. It's hard, it's tricky, but it's not as hard as it could be. Okay, this is a clicker we'll start with for today. So if you have a clicker, get ready to do it. If you don't have clicker and you haven't signed up or your clicker isn't working, just email me the answer. Okay, so the pH at the equivalence point of a strong acid, strong base titration is, don't overthink this. Hurry, hurry, Daniel, join the clicker. Oh, yeah. Well, I'll give people, once again, just send me an email or whatever if it's not working. I'll give you like till 2 minutes. 2 minutes. Okay. So, pH of strong acid, strong base. And we are. So, by definition, a strong acid, strong base is pH at 7, where the acid neutralizes the base. Remember back last chapter, for a strong acid, strong base, the conjugate acid of a strong base is a salt. The conjugate base of a strong acid is a salt. So when they're neutralized, there is no backwards reaction. So there is no, it's just a salt. It's not going to reverse. So it's going to be perfectly canceled out. So, okay. Now we will look at this, even though we won't do the calculations for this, we will look at this. And that titrating a weak acid with a strong base or weak base with a strong acid, it looks very different. I mean, you still see this kind of sinusoidal curve, but there is some numerous changes that will make this obvious that this is not the same. And this is going to be useful for say, oh, it's a weak acid, and you can tell something about it. In fact, lab number 3, where there's a titration with, sorry, lab number 4 of this virtual lab series, where there's a titration, we'll be actually graphing this and using this graph in order to like determine a lot of stuff about this. Oh. But okay. So first thing you'll notice is that the pH starts a little higher off than you would expect for a strong acid. So instead of being starting at point something, like over here close to 0, we actually see something closer to 2 or 3. But that by itself doesn't necessarily mean you have a weak acid. You could just have a very dilute strong acid. The next thing you see is you see a pretty sizable change under the first couple mils, and then we get the region where there's gradual increase, but not a big change. Big change right here, and then it kind of just slowly tapers off. This is our buffering region, where the pH is not allowed to change by very much, as it can go one way or the other. But we still get the same equivalence point. So the equivalence point, we still see a sharp jump at the equivalence point, but there's something different. Now, if you look here, 7 is here. The equivalence point for this weak acid is actually over here around 8 or 9. So the equivalence point of a weak acid is always above 7. Why is that? Well, when all of the acid has been neutralized in a weak acid, you're left with a conjugate base. The conjugate base is allowed to act basic in the presence of water with no acid. So we have this side reaction. The A minus, the conjugate base, will deprotonate some of the water to form hydroxide. And so we generate a little bit of naked hydroxide, which is going to make the equivalence point actually be basic instead of pH 7. Now we're going to have the same thing going on for a weak base. Weak base will form a conjugate acid at the all conjugate acid at equivalence point. And so the conjugate acid will deprotonate some and create a pH below 7. So instead of being at 7, it'll be below 7 for a weak base. And of course, because if we're titrating with a strong base and acid, the end of it just looks like normal. But so the very beginning part of it is the interesting part. Now, because of this weak acid, weak base scenario, and because of the nature of the buffering region, there is another point on this curve that we can read that's super important besides equivalence point. So if this is the equivalence point, 25, there's something known as the half equivalence point. Don't overthink the meaning. Literally, the half equivalence point is you take the volume at equivalence point and you half it. So half of 25 would be 12 and a half. You just take 0 mils, 25 mils, half of it. If this is 20, half of 20 is going to be 10. If this is 50, half of 50 is going to be 25. Whatever, half of the amount before the big jump, that's our half equivalence point. Now, why is this half equivalence point actually important? Well, that's because of the buffering region. The buffering region is described by pH equals pKa log of A minus over HA. Now, the half equivalence point literally means half of our acid is neutralized. Half of our acid being neutralized means it's formed half of the amount of conjugate base. So the amount of acid is equal to the amount of conjugate base remaining. When these two are equal, you divide A minus by HA, and they're equal, they give you log of 1. If you try to do log of 1 is 0. So what happens is this whole term drops out at the half equivalence point, and we have this neat thing that the pH is equal to the pKa of our weak acid.
Isn't this the same formula for the buff? This is the same buffering formula,
Yes,
isn't it?
it's saying at half equivalence point, this part drops out. So, and that's true for every single weak acid, weak base. At the half equivalence point, right here, pH equals the pKa. So now, because this is a base, this is going to be the pKa of our conjugate base. But we can use that to find the pKb just fine and dandy. So, but by using that, we're allowed to find the pKa and the pKb of our base. So even if or for our acid and our base. So even if we don't know what the acid is, we can actually try to determine what is the acid by looking at the pKa, by determining that from our half equivalence point. So
how do you find pKa again?
So it's literally, if this is our equivalence point at 25 mils, you take the half volume, 12 and a half, draw the line up, draw the line over. Oh my, that appears to be pH 5. So pH is 5, our pKa is 5. Literally, you read it off the graph. So in the analysis of a weak acid, a lab, which is the last one I've posted, there's still one more to come. You're going to be trying to find out what is the Ka 3 different ways. The third way is you literally look, I do a titration and I give you all the volumes and all the pHs, and you're going to plot that, and you're going to find where's my equivalence point, and then you're going to say where's my half equivalence point or thereabouts, and then you're going to say what is the pH at that half equivalence point. If you do that, then you found the pKa. Okay, let's look at what's on the next slide. Okay, yeah, we will not be doing this. We will not be doing this calculation. Basically, it would be the same calculation we'd be doing before, but we'd have to throw in all the weak acid, weak base stuff, and it's going to be a pain in the ass, and we will not be doing that. Nope, nope, just no, 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 and no. Lots of no. Okay, I'm going to go ahead and end this meeting right now. and I will start up the next meeting. So, and I'll give you guys 5 minutes to come and join the next meeting. And then we'll try to finish this chapter. So, sorry to say, Zoom meetings has not sorted out the whole thing with giving me the proper amount of time. So, I'll see you guys in a few minutes.
Okay, can you repeat one more time from the last meeting what we're not doing?
We are not.
Titration that we're
Yeah,
not
we
doing?
we are definitely. I'll tell you what we're definitely not doing any weak acid strong base or weak base strong acid titration calculations.
God,
So,
Caitlin, can you not remember that?
so we may, let's jump back. We will probably look at titration curves for strong acid, strong bases. We will probably look at titration curves for weak acid, strong base titrations. We may cover pH titrations of acid and base calculations. So strong acid, strong base calculations. We may see that on the test. We may not. I have not written the test. I'm not sure what I'm going to put on the test yet. But we may see that. But I'm going to tell you right now, I am not going to make you do any calculations with weak acid, strong base.
God, Caitlin, were you not paying attention?
But it's basically because you would have to do everything you would have done normally, but then instead of just the concentration of acid is equal to the amount of our of the acid remaining, we'd also have to take into account the amount of A minus. Whether if you neutralized some of the acid, you would have formed some A minus, and that would have made a buffer. If you would have done there's a whole bunch of like 100 other type, like not literally 100, but like 3 or 4 other calculations you would have had to do in addition to everything you would have had to do for a strong acid, strong base. So we're just going to say, nope, not going to worry about it. We're not going to do that. Had we maybe had another week, sure, but we're going to cut that off and just say, lost on the wayside of disaster. Yep. So, okay. Okay, let's just look. We probably won't see these, but it's good to know about these polyprotic acids. So when you look at a polyprotic acid, I'm saying things like H2SO4, H3PO4, H2CO3, anything with more than one proton that could be lost. Now, we won't worry about actually doing any calculations with these guys, but so you might see something like here, where you notice here, the equivalence point, you will see multiple equivalence points relating to the loss of all of the acids. So, for example, this is a diprotic acid. You see, here's the first titration point to neutralize the first proton, and then at double the volume, it's the amount we need to neutralize the second proton. The first loss, it's still acidic. By the second loss, it's now jumped into the basic region. So the equivalence points will be relating to the complete loss of each. Now, in practice, the second equivalent point should be double the first, but may not always be the case, just because some error. But what we note is there's a half equivalence point for each one. And as long as these are weak acids and not strong acids, you can get the pKa for the first loss and the second loss based on the half equivalence point. So half equivalence point of this guy would be 12 and a half. But this one might actually be a strong acid, so you might not be able to really see one. But this guy, this region, the half equivalence point between 25 and 50 would be what? 37 and a half. This guy where pH equals pKa is definitely the pKa of the second loss. So we can't, remember, we can never, ever, ever use the half equivalence point to find a Ka of a strong acid. So if it's a strong acid at the first loss, you're not going to get a pKa. And so if you're given a graphical problem, here's how we're going to approach this. First, figure out what we're titrating with what. Is it starting acidic or starting basic? That's always a good thing. So are we adding acid to base or base to acid? Step 1, determine the pH at equivalence point. If it's 7, then it's a strong acid, strong base. If it's less than 7, then we have a weak base. If it's greater than 7, then we have a weak acid. Step 2, determine the concentration of the unknown, whether it's acid or base, by using the volume at the first equivalence point. So you MA, VA equals MB, BB. So don't overthink that part. But when I give these problems on tests, people forget about that. That is chapter 4 stuff. That's general chemistry stuff. And we keep on reminding you, but people sometimes forget. If I know the moles of acid, I will know the moles of base at equivalence point. Step 3, if it's a weak acid or weak base, determine the pKa or pKb. If it's not a weak acid, if it's a strong acid, you skip this step. If it's a polyprotic, determine the second or third pKa. If it's not a polyprotic, you skip that step. So that's pretty much all you can do with a graphing problem. You don't have to overthink it. You find out what's being added to what. You determine if it's strong or weak, and you determine this. That's what you always do. Step 1 and 2 is what you always do. And if it's weak, we can do step 3. There's multiple jumps. We can do step 4. So looking at this one, I titrated 25 mils of acid with 0.75 molar base. And this is the volume of base added. So looking at this. So step 0, it starts acidic. So I'm adding base to acid. Step 1, where's the equivalence point? So about halfway between this jump is about there, which I draw the line over. That's about 8.9 something. That's clearly above 7. So is this a strong acid or a weak acid? Well, you should say it's above 7. It is a weak acid. Okay, with that in mind. Step 2, what is the concentration of our weak acid? So I look here. Hopefully you'll see about that point is about the equivalence point. So it's about 20 mils. 20 mils of base have been added. So MB, which is 0.75 times 20, is going to be the moles of base. Now we need to find, and that's also going to be moles of acid. So we take that volume, that 0.75 times 20, and we divide by our 25 mils of acid to find what is our molarity of acid.
Are you doing the math on a different screen? Or are you just going through it with this, like just talking?
I'm just talking right now. I'm not actually going through this because, I mean, I can pull it up.
I just wasn't sure, like, if you were on a different screen or not.
No, I was not. No, I'm not. I'm just working out through because this is pretty. Yeah, this part's pretty straightforward. This one is very little math. So I just say 75 times 20 divided by 25, and that would give us our MA. And that MA is 0.6 molar. So 0.6 molar acid. Now, since it's a weak acid, half of 20 is 10. So pH equals pKa at 10. I'm going to say this is where you have to make a little bit of an estimate. Say maybe 4.2, 4.1. So 4.2 is our pKa. The last step is, what is the Ka? Ka equals, I'll go ahead and pull this up on Paint, just so, Ka, remember, I gotta put it, pKa is equal to the negative log of Ka. So if I say this is 4.2, how do I get Ka? Well, I'm going to say Ka is equal to the negative log, 10 to the negative pKa. So I'm going to say Ka is equal to 10 to the negative 4.2. So with that in mind, our Ka is 6.3 times 10 to the negative fifth. 6.3 times 10 to the negative fifth. And that's what we get. Now, as I said, if you said 4.1, you would have got a slightly different number. And that's okay. On these type of problems, there is some amount of leeway with what you get. As long as you're not saying, oh, it's clearly pKa is 5 or pKa is 3.7. I mean, as long as you got it somewhere close by to where you should expect, you should be able to get points for that. So, okay. Now, here's the clicker question, clicker number 4. Identify the region of the titration where the curve is in the buffer region. Is it going to be A? Is it going to be B, C, or D? Where is our titration buffered? So, once again, if your clicker's having trouble, feel free to email, sort that out.
Can you explain how you found the pKa?
The pKa is always, for a weak acid, is always equal to the half, pK equals to pH at the half equivalence point. So I'll use this one in a minute. I'll use this one in just a minute once we finish up.
Okay.
To look at it again. Click away. I'll give you to the 2-minute mark. And I'm sorry that for those where the clicker is so sensitive that it like grabs the first thing. Doesn't let you change it either. Email my okay. Okay. So the buffering region, hopefully, B. It was B. So this one is all weak acid, no conjugate base. This one's all conjugate base, no weak acid. This is all strong base. So, and this is the region, the buffering region, where there's some amount of weak acid and some amount of weak base, where the amount of weak acid is decreasing as the amount of conjugate base is increasing. So this is 100% HA. This is 100% A minus. The buffering region is when you have some fractional amount of each. Now, how this works is that if this is 100% A minus and 0 HA, and this is 0 A minus and 100% HA. The point in the middle, which is the half equivalence point, when you have 50-50 of each. When they have 50-50 of each, they cancel out. And so the Henderson-Hasselbalch says pH equals pKa. So it's basically, if you're looking at the Ka expression, you're saying Ka equals H plus times A minus over HA. If A minus and HA are the same numbers, they cancel out, and you just get Ka is equal to H plus for that region. And that's always true for all weak acids and weak bases.
So the buffering system where it has a little bit of base and a little bit of acid.
A little bit of base, a little bit of acid. A little bit of weak acid, a little bit of weak base. When you get the strong base region, no buffers left. So it moves gradually, but it's not as gradual as this. But this is our equivalence point region, and there's our no acid, no base added. Okay. The last topic we'll talk about is KSP, or salt precipitation. This KSP stands for solubility product. So some salts, as we know, are insoluble. Silver chloride, magnesium hydroxide, iron carbonate, all these guys, not super soluble. We first introduced this in general chemistry as rules. You say, well, chlorides, bromides, and all halides are soluble except for with silver, mercury, and lead. And you had a chart, and there's some stuff behind it. But you were just like, oh, if I've learned this fact, I know what if it's soluble or not. Well, there's actually a K expression behind this that if you can actually mathematically predict how soluble something is. Yay. So the solubility is determined by the solubility product expression that allows how much salt could physically dissolve. Now, when we say insoluble salt, we're saying the KSP is really, really, really small. So small that we only get microscopic quantities of this salt to dissolve. So there's a solubility product for sodium chloride, but it's pretty big because we know salt dissolves in water pretty well. But silver chloride, not so much. So for a given reaction, silver chloride solid goes to silver plus and chloride minus. Remember, KSP, for a K expression, we do not include solids or liquids. So what part would only count? The only part that counts is this guy and this guy. So the solubility only depends upon the aqueous and gas phase components. So what that means is the amount of silver and chloride in solution there's only a set amount that will dissolve at a given temperature, regardless of how much solid is present. I haven't given the test back, last one, but there is when the Le Chatelier's principle, when you added a solid to component, the solid will not change the concentration. When you add more solid, if it's already fully dissolved and it's at equilibrium, adding more solid will not change how much product you form. So if this is already all of the silver chloride will dissolve, if I add more silver chloride, more won't dissolve. It's going to be saturated. So the only way to increase the solubility is 1, change the temperature. 2, change the volume. So if you have more volume, you're going to lower the molarity of everything involved, and so more can dissolve. Or 3, decrease one of these ions through Le Chatelier's principle. So if some of the chloride gets used up and put into something else, then suddenly more silver chloride can dissolve because KSP is related on the concentration of this times the concentration of that. Now, so with this guy, KSP, this is the KSP for this solution, 1.8 times 10 to the negative 10th, meaning that the maximum amount of concentration of silver chloride allowed in solution is 1.3 times 10 to the negative 5th molar. Pretty small. If I turn molarity into moles into grams, that would mean I can dissolve only 1.9 milligrams of silver chloride in 1 liter. So some of the homework problems use the density or solubility in grams per liter. But how would you turn that into molarity? Remember, grams divided by molar mass gives us moles. Moles divided by volume gives us molarity. So don't forget your roots. Don't forget where we came from. We can turn grams to moles just as easily as we can deal with molarity. Okay, so how would we go about calculating that? Now, it's like the ice table, only it's a little bit easier. Now, you note the ice table, initial, since this is a solid, it doesn't matter. How much is going to be these guys? Well, they're products, so it's 0. So the change, that's still going to be plus x and plus x. So at equilibrium, this doesn't matter, and we have x and x. So for silver chloride, KSP is equal to x squared. So if I did the square root of KSP, I would get the concentration of silver and the concentration of chloride, which is our, going back, 1.3 times 10 to the negative 5th. But how would we do something crazier like lead chloride? So remember, when we do the ice table, you add x, but because there's 2 chlorides, you get double it, 2x. So x and 2x. Now, the KSP expression is products over reactants raised to the power of their coefficients. Since it's 2 chlorides, that's chloride squared. So the KSP is x times 2x squared, or 4x cubed. So to do this, I'm going to take 1.75. So 1.7 times 10 to the negative 5th. I'm going to divide by 4, and then I'm going to cube root that. I'm going to cube root that to get our x. Our x is the concentration of lead, which is 1.6 times 10 to the negative 2nd. Now, because chloride is equal to 2x, we have to double that. 3.2 times 10 to the negative 2nd. But you're essentially solving for an x of the situation. It's a very easy KSP. The hardest part is thinking about this KSP and forgetting about our acids. It's the products without the reactants, but it's not really that hard if we break it down. So let's look at barium sulfate. How much barium sulfate would dissolve if the KSP is 1.08 times 10 to the negative 10th at room temperature? So barium, so let's select all, so I can delete this. So barium 1.08 times 10 to the negative 10. Okay. So with that in mind, barium splits into barium 2 plus and sulfate 2 minus. Don't get chop happy and split this any further. Barium and sulfate. So with that in mind, that's going to be equal to x. That's going to be equal to x. Our KSP is going to be barium times sulfate, or x squared. So if that's 1.08 times 10 to the negative 10th squared, square root this, square root this. So the amount of barium sulfate that is allowed to dissolve is equal to 1.04 times 10 to the negative fifth. 10 to the negative fifth. That's the concentration of barium. That's the concentration of sulfate that you would see in solution. Now let's see. Well, we will go ahead and we'll go ahead and work through one more problem. This one's a little bit harder. It's lanthanum trifluoride. Lanthanum trifluoride. So that one's a little bit hard. This one's ridiculous, and we'll never see this on a test. But lanthanum trifluoride splits reversibly into lanthanum 3+ and 3 fluoride minus. Our KSP expression would be lanthanum fluoride cubed. Okay. We got everything we need for this. Well, except for what is the KSP? The KSP is 2e to the 19th. 2e to the negative 19th. Okay. So our ICE table, ICE, for the LaF3, that doesn't matter. La and 3F, we're going to have 0, we're going to have X, and we're going to have 3X because we have 3 fluorides. Okay. So with that in mind, KSP is equal to X times 3X cubed. 3 times 3 times 3 is 27. So you get 27x to the 4th is equal to our KSP. So now we're going to take our KSP, which is 2 times 10 to the negative 19th, and solve for x. Step 1, I divide by 27. Step to get, so 7.4 times 10 to the negative 21 equals x fourth. Then I fourth root, and I get x as 9.27 times, well, 9.28 times 10 to the negative 6th. So this is 9.28 times 10 to the negative 6th. Now, because fluorine is 3 times x, this would be 2.78 times 10 to the negative 5th. Because we got to remember our x and 3x. So, whereas what's the concentration of LaF? Well, we figure out La, and then we figure out F. And so we will go ahead and finish up there. We'll do the last clicker question on Wednesday, finish up this chapter, and start talking about maybe some homework problems and looking at an old test or something like that. Okay. So